In the last lecture, we have discussed the motion of planets on the basis of Einstein's theory of gravitation. In other words, you can say what will be the planetary orbit, what is its differential equation. All these things we have seen earlier in my previous video on the basis of Einstein's theory of gravitation. Okay. Now, today we are going to see a very important problem, and this is regarding the crucial tests in general relativity, or you can say the crucial test in the Einstein's theory of gravitation. Is Einstein theory of gravitation correct experimentally? It was a vital problem. So definitely, whenever a theory is developed, we must have to test such a theory by experiment. And if the theory is in accordance with the experiment, then it is a valid theory. So there was a need to test Einstein's general theory of relativity, and you will see later on, finally it was found that Einstein's theory agrees with the experimental result. How we can test Einstein's theory of general relativity? Actually, there are three important consequences of Einstein's relativistic theory of gravitation. And what are those three important consequences? These are, first one is the advance of the perihelion of planets, particularly the planet Mercury. Okay. The second one is the bending of light rays in gravitational field. And the third one is the gravitational redshift of spectral lines. One thing you should note here, that in accordance with the classical Newtonian theory, there is no advance of perihelion of planets, there is no bending of light rays in gravitational field, and there is no gravitational redshift of spectral lines. All these three important phenomena cannot be described in terms of classical Newtonian theory. But Einstein's relativistic theory is able to discuss all these three important phenomena which is observed in practice. Okay. So if you test that there will be an advance of perihelion of planets, there will be a bending of light rays in gravitational field, and there will be gravitational redshift of spectral lines in accordance with Einstein's theory, which is experimentally seen, then you can say that Einstein's relativistic theory of gravitation is experimentally correct. And this is the aim of this lecture. But if I will discuss all these three phenomena in one lecture, in one video, that will be a very long video, very lengthy. Therefore, I will divide this lecture in three parts. Actually, in each lecture, we will discuss only one phenomenon. So in this first lecture on the crucial test of Einstein's relativistic theory of gravitation, we are going to see the phenomena of the advance of perihelion of planets only. In second lecture, we will see this second one, and in third lecture, we will see this third one. Okay. In fact, as I have told you that all these three consequences of general relativity have been experimentally verified, and therefore these are known as the experimental or crucial test in the theory of relativity. Okay. Moreover, these phenomena also provide a means to compare the relativistic theory of gravitation with the classical Newtonian theory. Okay. So now let us start to discuss the problem of the advance of perihelion of planets. And for this you will need the starting equation which we have obtained in my previous video when we have discussed the problem of planetary orbits or planetary motion on the basis of Einstein's relativistic theory of gravitation. If you recall what we have learned in my previous video, definitely you will see that the equation of orbit of a planet is given by this equation: d2u by d phi square plus u equal to m over h bar square plus 3mu square. Are you recalling this? Definitely you can recall because you have just learnt in my previous video this equation. Okay, and you have seen that in this equation this variable u is directly related to r, and u is given by reciprocal of r, that is u equal to 1 over r, and this h, which is actually a angular momentum of the particle or planet per unit mass, and in relativistic theory this is defined as r square d phi by ds. Actually here ds is the measure of proper time interval. Okay, in Newtonian theory at the place of ds there is dt, but in relativistic theory h, which is angular momentum per unit mass, or it is a constant of motion of a particle moving in a central force field like gravitational field, that is equal to r square times d phi by ds. Okay, now actually as a first approximation you can neglect this term 3mu square in comparison to m over h square, because you have learnt in my previous video that this quantity 3mu square is negligibly small in comparison to m over h square. So as a first approximation, let us neglect this term 3mu square present in the equation of orbit of the planet. Okay, and after neglecting it, the equation of orbit of the planet becomes d2u by d phi square plus u equal to m over h bar h square. And you know, we have also seen in my previous video that this equation is nothing. This is simply the equation of orbit obtained in Newtonian theory. Okay, so when you neglect that extra term or the additional term 3mu square, the result is simply the result obtained by Newtonian theory. Okay, and definitely you have studied the problem of planetary motion in the chapter central force motion in central force field. And if you have not an idea, I will suggest you go through my videos in the playlist Classical Mechanics, where I have discussed the equation of orbit, the problem of planetary motion, all these things. And there you will get the solution of this equation. Actually, this is just equation of a simple harmonic motion, you can say, and therefore this equation actually corresponds the Newtonian equation of motion for the planetary motion, or you can say the equation of differential equation of orbit, which is actually a second order differential equation. And when you will watch my video in classical mechanics on this problem, you will get the detailed solution of this equation. So on the basis of my video provided earlier in classical mechanics, I am writing here directly its solution. Okay, so the solution of this equation 2 is given like this. This is given as u equal to m over h square times 1 plus epsilon cosine of phi minus theta naught. In fact, in this equation, this epsilon and theta naught are constants. Okay? In fact, epsilon, you know, is known as the eccentricity of the orbit. Okay, and sorry, theta naught is known as initial phase, or it is uh, also called initial longitude of the perihelion. When you say perihelion, that means the position of the planet uh, when it is closest to the sun. So this theta naught is the measure of initial longitude of the perihelion, or it is also called initial phase. Okay. Now, if your aim is to obtain the second approximation, then you must use this equation 3 in the second term of the RHS of this equation 1. That is, instead of this u, only in this second term. Here there is also u, but we will not replace this u by that value. Only in this second term where u is present, let us put this value of u, which we have defined in equation 3, which is simply the solution of this classical equation of orbit. Okay. So you can see, when we will make this substitution, our equation 1 will become like this. This is d2u by d phi square plus u equal to m over h square plus 3m times u square. But now u is equal to this much, so instead of u, let us substitute this value. And since there is u square, so this will be m square over h4 times 1 plus epsilon cosine of phi minus theta naught whole square. Okay. Now we will simplify the RHS of this equation to some extent. Let us see. The first term in RHS is at each. Okay. And this product 3m times m square over h4, this is 3m cube by h4, it is also at each. And the bracketed term has been simplified on the basis of the formula a plus b whole square. So this will be 1 plus 2 epsilon cosine of phi minus theta naught plus epsilon square cos square phi minus theta naught. Okay. Now let us multiply by this factor 3m cube by h4 to the terms inside this square bracket, and after multiplying by it, you will get this result. It is just an easy calculation. Okay. Now you can see in this equation, out of the additional terms, these are additional 1, 2 and 3. 3 terms are additional terms, because in classical equation of orbit, all these 3 terms are not present. Only this m by h square is present. Okay. So there are 3 additional terms, and among these 3 additional terms, only the term which contain which can produce any effect within the range of observation is the term containing this cosine of phi minus theta naught. Only this will be, its effect will be significant. Okay. Now you have definitely studied the theory of differential equation, and in a study of physics we have encountered at several places such an equation. You know, if we consider a differential equation like this, d2u by d phi square plus u equal to a cos phi, then its particular integral or its particular such type of equation has 2 solutions. One is called actually complementary function, and another is called particular integral. The particular integral of such a differential equation is given as u1 equal to 1 over 2 a phi times sin phi. Okay. Now this additional term, as I have told you that only this additional term will produce some effect, okay, on our result. So the additional term 6m cube over h4 times epsilon times cosine of phi minus theta naught, this gives a part of u, and that will be given by u1 equal to 3m cube over h4 times epsilon times phi times sine phi minus theta. Okay? And therefore you can write the solution of equation 1. Actually, this is the solution of equation 2, which was classical equation, and only the difference in solution of classical equation and the relativistic equation of orbit is this much. So when you will add this correction term in the solution of the classical equation of orbit, then you will get the solution of the relativistic equation of orbit, which has been defined in equation 1. So the solution of the equation 1 to the second order of approximation is given by this much: u equal to m over h square times 1 plus epsilon cosine of phi minus theta naught plus this much, which is actually the correction term. Okay. Now again we will simplify the RHS of this result to some extent. See here, let us multiply by this m over h square to the terms inside the square bracket. The first term will be m by h square, and now associate the second term. This will be m epsilon by h square times cosine of phi minus theta naught, and this term. Among these two terms you can take m epsilon by h square as a common factor, and when you will take it as a common factor, the remaining terms will be cos phi minus theta naught, okay, plus 3m square phi over h square times sine phi minus theta naught. Okay. Now we substitute delta theta naught instead of this factor 3m square phi over h square. This is written as delta theta naught. Actually, you will see later on that this delta theta naught is the measure of the advance of perihelion of our planet. Okay. But this delta theta naught is very small. This is a very small quantity. And since it is very small, and you know when theta is very small, sine theta and tan theta both are equal, and both are equal to theta. We have studied in the limit theory in calculus. So since delta theta naught is very small, therefore you can take sine delta theta naught will be equal to tan delta theta naught, and both are equal to delta theta. And in this limiting condition, you also know that cos delta theta naught is equal to 1. Okay. So now at the place of this delta theta naught, you can take either tan delta theta naught or sine delta theta naught. And if we will multiply the first term by cosine of delta theta naught, this will make no difference, because cos delta theta naught is simply 1. Therefore, that equation can be written as u equal to m over h square plus m epsilon by h square times cosine of phi minus theta naught times cosine of delta theta, because this is 1. So after multiplication by this factor, the result is unaltered. And here at the place of delta theta naught, I have written sine delta theta naught. Okay. But you know from the formula in trigonometry that cos A times cos B plus sine A times sine B, that is simply cosine of A minus B. Here at the place of A is phi minus theta naught, and at the place of B is delta theta naught. So the bracketed term can be written as, this can be written as cosine of phi minus theta naught minus delta theta. And now, if you will associate both of the terms in RHS and take this m by h square as a common factor, then at the first term there will be 1 and sorry, the page has been turned, but this will be just okay. Don't worry, because I am working with this iPad for a longer time, so it is hanged. Okay, but it is not a serious problem. You can see, and the remaining factor term is epsilon times cosine of phi minus theta naught minus delta theta. Okay, so actually this is the solution of the relativistic equation of the orbit, which you have defined in equation number 1. Okay, and this solution has been obtained under the second order approximation you have seen. Okay, now as I have told you earlier that this quantity delta theta naught which is present here, this actually corresponds to an advance in the perihelion of a planet. This is the measure of advance in perihelion. So you can see that the relativistic equation of orbit predicts that there will be an advance of perihelion in the orbit of the planet. But Newtonian theory does not predict any such advance in perihelion. In Newtonian theory, you know, it is said that the orbit of a planet is elliptical and it is fixed. The planet does not change its orbit. Okay, it always moves along the same elliptical orbit. There is no advance of perihelion or aphelion. Okay, but according to Einstein's theory, you can see that this u, which is 1 over r, that actually depends on this delta theta naught, which indicates that when the planet will move and it will be closer to the sun, that is at the perihelion position, then there will be some advance in the perihelion and the orbit will not remain a fixed ellipse. Okay, so it is obvious that when a planet moves around the sun through one revolution, if you consider that the planet moves one revolution, then it will rotate by angle phi. So the angle of rotation phi for one revolution will be 2 pi. Now, if your aim is to find how much there will be an advance of perihelion in the orbit of the planet after one revolution, how you can find it? You can find it easily from the defining equation of this delta theta naught. You know, delta theta naught is this much, and your aim is to find now the advance in perihelion of the orbit of planet after one revolution. And you know, after one revolution, this phi will be 2 pi. So when phi will be replaced by 2 pi, you will get the advance in perihelion after one revolution of the planet. Okay, so advance in the perihelion is given by the angle delta theta naught, and this will be 3m square over h square times 2 pi. This is the value of pi after one revolution, and so it is simply 6 pi m square over h square. Okay, now definitely in coordinate geometry you have studied in detail the idea of ellipse, and you know, from for an ellipse, this m by h square is equal to 1 over l. Here L is actually called the semi-lattice rectum of the orbit, and this is equal to 1 over square root of a square plus b square. Here a is the semi-major axis of the ellipse, b is its semi-minor axis, and it is in terms of eccentricity epsilon, it is given as 1 over a times 1 minus epsilon square. All these results I have written directly because this is the subject matter of the course in coordinate geometry on ellipse, and definitely you have studied it. Okay, so from here you can see that m over h square is equal to 1 over 8 times 1 minus epsilon square. So h square will be equal to m8 times 1 minus epsilon square. And therefore, when you will substitute this value of h square in this equation 8, you will get the advance in perihelion delta theta naught after one revolution of the planet. So delta theta naught will be then equal to 6 pi m square over h square. See here, but h square is this much. So after substituting the value of h square, your result is this. And here, one of the m will cancel out, and so this is 6 pi m over 8 times 1 minus epsilon square. Okay. Now, you have studied the Kepler's problem and the third law of Kepler's planetary motion. And according to third law of planetary motion, you know the square of the period of revolution of a planet is proportional to the cube of the semi-major axis, and therefore the period of revolution t is given by 2 pi over a square root of m times a to the power 3 by 2. Here 2 pi by root m, this is at the place of proportionality constant. And so from here you can find the value of m, this is 4 pi square a cube divided by t square. Okay. Now let us use this value of m, which we have obtained on the basis of Kepler's third law of planetary motion, in this equation number 9. Okay. At the place of m, we will substitute it. You can see. Then delta theta naught, this will be equal to 6 pi over 8 times 1 minus epsilon square times m. But instead of m, now I am writing this much. And now one of the a will cancel out, and your result will be delta theta naught equal to 24 pi cube a square over this much. This is actually the result for the advance in perihelion of the planet. And you can see, if you know the semi-major axis A for the planetary orbit, its time period t, and eccentricity of the orbit epsilon, then you can easily find the advance in perihelion of the planet after one revolution. Okay, you can easily find. Actually, this result is also expressed in terms of speed of light. Okay, so if you want to express this result in terms of speed of light, then you have to divide this by c square, and therefore in terms of speed of light, this is written as delta theta naught equal to 24 pi cube a square by c square times this much. Okay, so this is the relativistic result for the advance in perihelion of the planetary orbit. And you can see that the relativistic theory of gravitation proposed by Einstein leads to an advance of perihelions of the planetary orbits, which was not predicted by Newtonian theory. Okay. In other words, you can say Einstein's theory of gravitation leads to planetary orbits with a slow rotation of the perihelions instead of leading a perfectly closed elliptical orbit of the Newtonian theory. You know, this first figure, let us say this is figure A and this is figure B. In figure A, I have shown an elliptical orbit of a planet. This is your planet of mass m, and it is revolving around this, and this is the position of the sun. Okay, and you know, when we apply to discuss the motion of planet, the Newtonian theory, then in accordance with Newtonian theory, the orbit of the planet is fixed. It always revolves around this ellipse. There is no advance in perihelion. Okay. So Newtonian theory predicts a closed elliptical planetary orbit, as has been shown in figure A. But according to Einstein's theory, there will be a, a slow rotation of the perihelion. Okay, so Einstein's theory predicts a slow rotation of the perihelion of the planet, as you can see in this figure. Okay, here orbit is not fixed. When here there will be actually sun. Okay, and when the planet will be nearest to the sun, its orbit deviates from the original elliptical orbit. Okay, and that's why we say that Einstein's theory predicts the perihelion of the orbit of planets, but Newtonian theory does not predict such an advance in perihelion of any planet. Okay. Now, utilizing this formula A2 or A1, you can find the advance in perihelion of a planet in after each revolution. Okay, for any planet. But it is seen that when the value of delta theta naught is found numerically, that is when we calculate the advance of perihelion of planets, then except Mercury, the value of delta theta naught for other planets is negligibly small. But in case of Mercury, we get a significant value of delta theta naught. So it is also said that there will be an advance in perihelion of Mercury, that is very significant. Although there will be an advance of perihelion in case of all planets, but the value is very small, negligibly small. But in case of Mercury, there is a significant figure for the advance in perihelion. If you talk about the planet Mercury, then it is found that for the orbit of Mercury, the eccentricity is epsilon equal to 0.2056, and the semi-major axis for its orbit A is 6.0 into 10 to the power 7 kilometer, and its period of revolution is 88 days. When these data is substituted in the result for delta theta naught, which I have defined in equation A1 or A2, then it is found that delta theta naught is 43 second of arc per century. This is a detectable value. And when experimentally this the value of delta theta naught is obtained, it is seen that this theoretical value completely agree with the experimental value, since there is a complete agreement of the theoretical value with the experimental value. So it is a very crucial test for the validity of Einstein's theory of gravitation. Okay, so you can say that this advance in perihelion of Mercury particularly is a crucial test for the validity of Einstein's theory of general relativity. Okay? As I have told you earlier, that when the value of delta theta naught is calculated for other planets except Mercury, the value comes out negligibly small. Okay? And so sometimes it is not detectable. But nowadays, after the invent of electronic computers, it is possible to calculate the advance of perihelion of Earth and Venus too. Okay, by the use of computers. Okay, so you can see that actually the advance of perihelion of planets provides one of the experimental tests for general theory of relativity, and I have discussed only one phenomena in this lecture, but I have told you that there are three important phenomena or three important consequences of general relativity that can be tested experimentally. So, in the second lecture, our aim will be to discuss the another consequence, which is bending of light rays in gravitational field. Okay, and then after three lectures, the experimental test or crucial test of general relativity will be completed. I think you have definitely enjoyed this lecture. Okay, thank you very much.